Vertical circles. Vertical circles obviously act differently to horizontal circles. Horizontal circles, we always had velocity being constant, whereas of course it's changing for vertical circles. Some people think that makes it kind of trickier, and certainly they did used to be on Mechanics 3 rather than Mechanics 2 in the old modular exams. However, that's really because they just introduce a new bit of maths, mainly the energy. But as you know, conservation of energy isn't that tricky at all. It's a two-step process. We first of all, I think pretty much every time start off by looking at energy. We know by the conservation of energy that the gravitational potential energy plus the kinetic energy at any point anywhere on our circle is equal to the gravitational potential energy and kinetic energy at another part on the circle. So as it's going round, no matter where it is, energy is always constant. So that's the first task, looking at energies. And then once we consider the energies, just like with our horizontal circles, we use F equals ma. And that, of course, is because we always have our acceleration acting towards the centre of the circle. And as before, we're looking at a resultant force acting towards the centre. And what you find with vertical circles is there's generally fewer forces acting. And again, we've got our two choices of accelerations, one for angular velocity and one for speed. So the three questions today. This first one here, it's a question 6, and this was of a 7-question paper. And if you look, the last part in particular worth 8 marks. But the reason that I've chosen this one, even though the next one's got fewer marks, is because we've got this first one, we're just working things out numerically. So quite often in the first part of the question, you have to prove an algebraic expression or show an algebraic expression. So this one here, the first part, we have got a mass 0.4 kilograms. The length of the string is 2. It's going around in this vertical plane, and we know that that angle is equal to 0. Down there at the bottom, the speed is equal to 7. So we are asked specifically about when the string is horizontal. So I'm just going to draw another diagram here and making it clear what these 2 points are. So I'm going to refer to that as point A, and here's my horizontal. Let's make that clear with a right angle. That is my point B. We have the radius is equal to 2 meters, so let's mark that on there. So I'm going to start off by considering the energies. I think every single question, that's what we start off by doing. And I'm going to work out what's going on at A. I'm going to take my 0 level to be the bottom, and there it's generally good to keep things positive when you can. So I'm going to say that that's h is equal to 0. I also know that the speed is equal to 7, so v is equal to 7. So I'm going to write down my energies. Always make that clear, please. You know, put GPE plus KE. There's nothing much to it, really. Now, I'm sure you know this, but every time when you consider energies, mass is running all the way throughout. So don't be writing down the 0.4 in there. Just write it algebraically as m, and all of them are going to cancel out. That's 0. This gets me 49 over 2m. I said at there, but should we add on that A? There we go. Because I'm about to do what's going on at B. At B, the height is equal to 2. The velocity is what we need. So again, I'm making it clear what I'm doing. I'm writing down my energies. I've got mgh times 2 plus a half mv squared. So what we need to do is equate these two energies here. Why are we doing that? We're doing that by conservation of energy. 49 over 2m is equal to 2mg plus a half mv squared. And of course, as I said earlier, the m's all cancel, leaving me with 49 over 2 is 2g plus a half v squared. Let's multiply everything by 2. And so now we find that v squared is 49 minus 4g, and v is the square root. 49 minus 4g. I'm sure you've gathered that, you know, we've got 9.8 for g. That's a multiple of 4.9, which is 7 squared. So these all very nicely kind of cancel out, and you end up being able to express things in terms of g. So it actually turns out to be v squared being the square root of 9.8, which is 3.13 meters per second. So that's the speed. We now need to look at the tension. Now, what we have here, I've got, this is my particle P, I've got the weight acting down. So here I'm considering what it's like at that position. So it's at position B. It is accelerating towards the centre. So that's my acceleration arrow. And there's my tension. Because we've got a 90-degree angle there, of course, it means that no component of the weight is acting towards the centre of the circle. So the only force I need to consider is T. And that's acting directly towards the centre, of course. So I'm going to use F equals ma, but the only force we've got is T. And that is equal to m. And I am going to need to use the m now. It's 0.4. So 0.4 multiplied by a. Obviously, I'm going to be using v squared over r because we've worked out the value of v there. T is 0.4 multiplied by, well, I know v squared, that's 9.8, divided by r, which is equal to 2. And that gets me 1.96 newtons. Okay, so 4 marks there. As I said, a pretty standard thing. Energies, cancel the m's, and then consider your F equals ma towards the centre. Now, a little bit more exciting for the second part. So in part 2, the string becomes slack. So imagine as we go around here, sometimes you are travelling at such a speed that P would make it all the way past the top and back round. But of course, sometimes, you know, we know what happens in real life. It kind of gets up and then the string goes slack. The crucial thing, of course, because the string is slack, that means there's no tension. However, say it happens up here, the particle is going to still keep moving, so the velocity isn't 0. So it's important to understand that distinction. Tension is 0, but velocity isn't going to be 0. The other thing, of course, we know is that because it's got a velocity here, what was it? It was 3.13. It is going to keep going, but it won't reach the top. So it's going to be somewhere in this region here. It's going to be between theta being 90 and 180. We could take the horizontal and go at an angle theta above that. But what I think is more typical is to take the angle, you know, from the vertical. So I think it makes the components, you know, slightly easier, and it's more consistent with what happens in other questions. So I've put a different angle there. I've called that alpha. Of course, we know that the theta, which would be that one there in alpha, just add to 180. So I can just subtract from 180 at the end. So I've already started, and I said the string becomes slack. So we know as T is equal to 0. I'll call this C because we've got a different point now. Again, we start with our conservation of energies. I know that the height there, okay, I have got 2 meters there. And then I've got a further length there. So I've got the 2 meters and then I've got that other bit there. So my height at C is going to be 2 plus, well, I need to work out that little pink bit there. If I got that being alpha, then I'm going to have a similar angle of alpha there. So we can see that length is 2 because it's the radius, and I've got the adjacent component, so that's going to be cosine. So 2 cos alpha. I can then say that my energy, my total energy, is equal to mg multiplied by h, which is that 2 plus 2 cos alpha, and then a half mv squared. I don't know what v is. As I said, not going to be 0. And of course, we've already worked out what's going on at A. At A, I have got my total energy was, from the previous part, it was just 49 over 2m. And again, we equate these two. So I know that by the conservation of energy, I've got mg 2 plus 2 cos alpha plus a half mv squared is equal to 49 over 2m. M's will cancel. And then if I just expand this bracket, I've got 2g plus 2g cos alpha plus a half v squared is equal to 49 over 2. Can't do anything else with that at the moment because, of course, there's 2 unknowns there. So I don't know what alpha is and I don't know what v squared is. So we're going to have to put that to one side for the moment. And quite often in exam questions, you'll see in the ones we're going to look at shortly, you are given an algebraic expression to prove, and it's generally this method. So looking at energies, and you're left with an expression there with normally angles and velocities that we don't know. Okay, so now I need to move on to the second step. Resolving towards the centre of the circle. I know I'm going to be using F equals ma, but be careful with what we've got here force-wise. In the first part of the question, because it was horizontal, we knew that the 2 forces were perpendicular. So we had this situation here, we had that perpendicular force, the mass wasn't contributing anything towards the direction of the acceleration. Here, however, it is going to be. And if I just draw a little sketch, I know it's contained in there, but that was really for lengths. This diagram here is going to be to work out forces. So there's the string. That's the centre of the circle. This is part C. And here is my weight force acting down. So it's essentially this triangle here, but I've just drawn forces on rather than the lengths. T actually is equal to 0, but I've drawn that in because I can see the triangle and I can see where the string is. So let's just make a note there. T is equal to 0. So the weight component that I want, be a little bit careful here. It's tempting, isn't it, to think about this triangle there. However, what I want to consider is a triangle where the weight is the hypotenuse. So what I'm looking at is this triangle there, and possibly drawing that out again might have been useful. So that's the right angle. That's alpha, that is the weight, and actually the component I want is that one there. It's the one that's in the direction towards the centre. It's the cosine component because I've got my angle and that's the adjacent side. So when I'm using F equals ma, all I've got is mg cos alpha, and that is equal to ma. And because I've got a v squared in there, let's use v squared over, and the radius is equal to 2. Again, the m's cancel. G cos alpha is equal to v squared over 2. So it's a much shorter equation, a much simpler equation. And actually very nicely, that v squared over 2, v squared over 2, so I'm going to put g cos alpha in there. So substituting these, I end up with, I've got my 2g plus 2g cos alpha plus, instead of half v squared, I'm going to have g cos alpha, and I've got the 49 over 2 on the right hand side there. 3g cos alpha is equal to 49 over 2 minus 2g. So cos alpha is 49 over 2 minus 2g over 3g. So I'm almost kind of keeping the algebra there. Sometimes you'll be asked to do this algebraically. I'm just going to pick up the calculator at the last stage. When you work this out, because of course that's really, in terms of g as well, we actually get 0.16 recurring, which is 1/6. All of the g's would cancel, leave me with 1/6. So alpha is equal to inverse cos 1/6, which is 80.4 degrees. The one thing I have to be careful, of course, is that we were working out theta, weren't we? We're asked to work out theta. Theta is there. So we just end by saying that theta is equal to 180 minus the 80.4 degrees, 99.6 degrees. Okay, 8 marks. Same method as before. Of course, the awkward thing is having this component here, having to resolve what's going on with that weight force.